All right, we're going to continue with section 2.1 here. We look at a little bit different of a problem. So it says, write the standard form of the quadratic equation whose graph is a parabola with a vertex 1, 2, and that passes through the point 3, -6. So first thing what we need to kind of look for is we need to actually see and remind ourselves what that actually looks like. What is standard form? So here, that looks like y equals a x minus h squared and then plus k. And so what we first have is we have this vertex. So that vertex point is that h and that k. So we know that h is going to be 1, and we know that 2 is going to be k. We're also given one more piece of information, which is this point. So the first thing I'm going to do is I'm going to take these values. Wherever I see an h, I'm going to plug in 1. Wherever I see a k, I'm going to plug in 2. So y equals a, and then x minus 1 squared, and then plus, erase that, and then that's going to be plus, and then a 2. So I got that. Now the next thing we have is up here. It gives us this point. We're going to act like any coordinate point. We know that that's x, and then that's y. So I know this x is going to go in here for this x. This y is going to go in here. Here's why. This is almost in standard form. So again, it's going to look like this. The only thing we need to know is what a is. So we're going to keep y and x as y and x because an equation like that with a quadratic is going to have a y and x. But we don't have an a there. We need to know what that a is. So maybe it's 1 or 2 or -5. Remember, that tells us if it opens up, if it opens down. With transformation of functions, we learned that a value is like a 3. That's going to stretch it vertically. If the a value is like a 1/2, that's going to compress it. That's going to make it look a little bit wider, whereas stretching is to make it look a little more narrower. So what's that a value? Well, that's where this is going to come into play. We're going to take this 3 and plug it into x. We're going to take this -6 and plug it in for y. So I have -6, plug it in there, equals a, this 3, I'm going to plug in here, and then that's going to give you 3 minus 1 squared plus 2. And now we're just going to kind of use some order of operations. So I'm going to leave -6 the same, equals, we're going to do this parentheses, 3 minus 2 gives you 2, plus 2. I can then take that, so that's a times 2 squared is 4, and I could go ahead and solve it. Well, the first thing I'm going to do is I'm going to minus this 2 to both sides. And that'll give you -8 equals a times 4. And the opposite of timesing by 4 is to divide by 4. So I divide those by 4, and I get -2 equals a. So I'm almost done here. I'm basically going to take this and then take this. So that a value of -2 is going to go right there. So my answer is going to be y equals what I just found up here, which is a. That's -2. And then the rest of this up here is going to be the same. So I'm going to have that parentheses x minus 1 squared and then plus 2. And that's how you, given the vertex and also a point, how you find an equation. So let's do another one. Same situation. So I know this again. This is going to be my h and my k. I know my equation is y equals a x minus h squared plus 2. So again, I'm going to take these values. This h is going to go here. This k is going to go there. I didn't even put that. And so then this, that k. So then I'm going to take that and kind of just plug it in. So once I do that, I'll have y equals a x minus a -5 squared and then plus 13. Now we know by now that minus and negative is really a positive. Then we're going to do what we did before. This is a coordinate point, x, y. So this y here, that's going to go there. This x, that's going to go here. So once I replace those, that gives you 22 equals a. We remember the whole point of this is to find what a is. X is a -2, so I get -2 plus 5, that quantity squared, and then plus 13. So 22 equals A. If I add these two numbers in the parentheses, -2 plus 5, that'll give me a 3. So then I get 3 squared plus 13. 22 equals A times 3 squared is 9, and then plus 13. Now, if I want to go ahead and solve this one, we get a minus that 13, minus that 13. That'll give me a 9. So I have 9 equals A times 9. And then to get rid of that timesing by 9, I divide. That gives me A equals 1. So like we did before, we're going to use this equation here and the fact that A is going to equal 1. So when I type that in, y equals 1, and then it'll be x plus 5 squared plus 13, or since that 1 there, if I have like an x or something, we never always write that 1. So we can either write it like that, or I can write it and just assume that we know that that 1's there. So it could look like this. So either one of those are acceptable. So there's a second example of that one. Now we talked in the last video about how there are applications. So let's say we have a path of baseball after being his modeled by this equation. So you see this is a quadratic. My highest exponent there, my degree is a 2. You can see that my A value is a negative, a small negative number, so it's going to be a little bit wider. It's going to be compressed. But the fact that it's negative means it's going to be reflected. So it's going to be like an upside down U. So this thing's going to, kind of something like this, where it's going to be going up and then coming down, which kind of makes sense. And f of x is the height. So the y value is the height, and then the x value is the horizontal distance from home plate. So there's two ways to do this. You can take this equation. You can use the standard form to find the vertex and see the max height. That's the y value. So on the last video, when we kind of completed the square, that y value would be the max height. The x value would be how many feet it's gone at that point when you're at that max height. The second is to graph it and see the max height. So we've already talked about this and how to do this on the last video, so we'll just be able to graph it. So let's say I graph it. It looks like this. Now we only care about once, the domain of this function is, hey, once it's being hit, so at my, distance right here of 0 until how far it lands, and after that we don't care about. So the domain on this real world problem is just from 0 feet until where it hits, and that's something in 3, 10, or 20 or something along those lines. So this thing ball is going up in the air and then it's coming back down. So we want to be able to say, again, the question says, what is the maximum height of the baseball? So on desmos, if you graph it, this is what you look like. But you have to click around and say, hey, what's that max height? What's this information right about there? What's that coordinate point? So just click it. So if I do that, that's what I get. So in this case, my max height is this. So the max height is 81.125 feet. That's the max height. Is that. Now, the other thing to look for that it doesn't ask before, but this problem right here. So the domain in this case is from 0 feet all the way to where it hits the ground, which is 315.472 feet. So if the question said how far did the ball go, that's what this is. So again, picture that ball going up and coming back down. It's not going through the ground and digging all the way through to the core of the earth or anything like that. It's going up and then coming back down, then stopping, and that's all we care about, which is why we talk about that domain. So for this question, the answer is 81.125 feet. But if it did ask you the question, how far did the ball go, then that's where this 315.472 is.